I meant to hit record. Okay, so I'll show that apparatus again later on, but here, let me just put a mark. I got some painter's tape. You can see like the rate at which gas is made. We'll put an arrow. That's okay. So there's the mark on this side. Here's that really good. So that's where the two gas volumes are at the beginning of the period. So we'll find out at the end of the period where they are. It's easy. It's hard to see it on the video, but those, it's like the gold Sharpie, or silver. That's gold Sharpie. But silver Sharpie turns out to look pretty good on there too. Okay, let's see. This is, what is that stuff? All right. So there's a whole bunch of gas laws, and they relate volumes, temperatures, pressures, quantities of gases in different kinds of ways. And besides these four gas laws, which are actually really only one gas law, there's another gas law called the ideal gas law. And between the ideal gas law, Boyles, Charles, Gay-Lussac's law, the combined gas law, and Avogadro's law, you can relate quantities of gases. So here's the whole story. The story is that it's difficult to work with gases in chemistry. When you work with solids and liquids, if you want to know the mass of a solid, you just throw it on the balance, and you got the mass in grams. You convert it to moles, you're done. If you want to know the volume of a liquid, you just throw it in a graduated cylinder. You read it on the cylinder, you're done. With a gas, gases are compressible. You can squeeze them down. They can expand to be larger in volume. And as a result, that thing about Avogadro's law, where, like 1 mole of gas has a volume of 22.4 liters, that's only at STP, or standard temperature and pressure conditions, which, is like standard temperature is 0 degrees C and standard pressure is 1 atmosphere. But if you change the temperature of the gas, it's going to change the volume of the gas, and that 22.4 liters is no good anymore. You can also compress the gas to take up less space. And then the pressure goes up. And as a result, you got more gas in a smaller space. So then that rule doesn't work. So the only time Avogadro's law, which we have used so far, only works at standard temperature and pressure. So of any kind of quantity that you have to measure in chemical reactions, gases are by far the most difficult to deal with. And then a lot of chemical reactions produce gases. So this chemical reaction here, that electrolysis apparatus, if you want to look it up, it's called the Hoffman electrolysis apparatus. Electrolysis means to use electricity to do some kind of a synthesis or some kind of a change. In this case, the decomposition reaction. I'm taking H2O, which is a liquid, and that liquid decomposes to make H2, which is a gas, and oxygen, which is a gas. So to measure the volume of the liquid, or measure the mass of the liquid, you can like throw it in a graduated cylinder, throw it on a balance, but then you get these gases, and depending upon the conditions, so room temperature is not 0 Celsius. The only time that gas in that container would be at standard temperature is if this room was at the freezing point. It'd be 32 Fahrenheit. We don't keep this lab at 32 Fahrenheit. That's not how you do science most of the time. So as a result, the volume of the gas in there is not 22.4 liters per mole. It's a bigger volume per mole. And then also atmospheric pressure varies from day to day. So, and I can tell you, I can guess that atmospheric pressure is lower than standard atmosphere pressure right now. I know that because there was a little bit of rain on the sidewalk this morning. And when it's rainy, that's indicative of lower atmospheric pressure than normal. If it was a bright, sunny, nice, warm day, that would probably be higher atmospheric pressure. So atmospheric conditions in terms of precipitation and clarity of the air is highly dependent upon what the pressure of the atmosphere is. That's a big deal. Like you take a meteorology class, there's a lot of stuff about gases, because really like the atmosphere is just a big gas law problem. All right, so here's the deal. There are different laws related to gases, and there are two different kinds of gases, ideal gases and real gases. So what it means to be an ideal gas, there are some postulates about ideal gases you can read about like in your textbook. And that's that all the molecules in a gas are all uniform in composition. There's an equal mixture of, but there's a 100% composition of one individual gas. The collisions between the molecules are perfectly elastic. The collisions between the molecules and the container walls are perfectly elastic. There's nothing besides the individual gas in the mix. There's a whole bunch of conditions about ideal gases. And also, a standard ideal gas is a gas that is at 1 atmosphere of pressure and a temperature of 0 Celsius. But because you got all kinds of different temperatures and pressures, you end up with different problems. Okay, so here's some things to know. We measure pressure using a bunch of different units. If you watch the news or read about, atmospheric pressure in meteorology, there's a unit of pressure that's INHG, which stands for inches of mercury. And I'll show you about the design and construction of barometers. But barometers traditionally use a column of mercury, and the atmosphere can support a column of mercury of a particular height. And our atmosphere can support a column of mercury that's about 30 inches. So in common everyday language in our country, especially in meteorology, when you're talking to Americans, you talk about pressures in inches of mercury. But in science classes, we don't use inches. We always use the metric system. But because there are different kind of sciences that use gases, different people have adopted different pressure units. So the most fundamental unit of pressure in all of science that's related to the height that a barometer can hold is this unit. It says mmHg. That stands for millimeters of mercury. So here's what that refers to. If you take a container, like a dish or a pan, and then you place into that container a tube that's upside down and that's covered at the top, and then inside the container, you've got mercury in here and mercury in the column. The deal is that all of this green space is all mercury. Mercury is a very, very dense liquid that's a metal. It's the only liquid metal, and that's why mercury is used in making barometers. And then this space up here is vacuum. So the deal is that our atmosphere can support, we say support, a column of mercury that is about 760 millimeters tall. 760 millimeters is 3/4 of a meter, about that tall. We don't have a mercury barometer here in school anymore. We used to have a really nice wall-mounted mercury barometer with real mercury in it. It was legit. We had an issue with mercury one year with a big spill, and we evacuated the school and had to do a whole cleanup and the whole thing. So we've gotten rid of all of our mercury. But I'll show you, I got a link to some good videos about the designs of barometers. So the deal is that our atmosphere can support a column of mercury that's about 760 millimeters tall. And that pressure, the standard pressure of our atmosphere, comes about because the atmosphere is actually pushing down on this container of mercury, and that mercury can be forced up into the tube. So the pressure of the atmosphere pushing down on the container forces mercury up in the tube so long as this is vacuum up here. And that pressure of the atmosphere is also another unit called ATM, or the atmosphere. So this 1 ATM stands for 1 atmosphere. The atmospheric pressure comes about because, like, you live at the bottom of an ocean of air. There's all this air that's above you, and the weight of all that air above you pushes down it exerts pressure on you. It's the same as like if you go into a swimming pool or in a lake and you swim down in the water, you can feel that water pressure increase and push on you and squeeze on you. So you're kind of not aware of the pressure of the atmosphere because you were born in it, you live in it, but the atmosphere plays an important role in keeping you alive because it's atmospheric pressure that's able to push oxygen into your blood for you to be able to survive. If you decide that you want to climb to the top of Mount Everest up through a large portion of the atmospheric pressure is much less, and it's very difficult to bring in enough oxygen. So most like high altitude climbers take supplemental oxygen. They breathe oxygen, it's pure in a tank. So these are conversions that you got to be familiar with. 1 atmosphere is a unit of pressure that's related to the pressure of the atmosphere of the Earth that it typically is like in regular laboratory conditions, except that pressure can change depending upon your altitude and the weather conditions. This 760 millimeters of mercury is what we standardized to be the height of a column of mercury that can be supported by an atmosphere. And then this other unit here, something you've never like worked with before, kPa. So K is the prefix for kilo, just like you can have a kilometer or a kilogram, and then PA stands for Pascal. So what you need to know is this unit is called the kilopascal. And fundamentally, a pascal is a unit of pressure that's equal to the Newton per square meter. A Newton is a unit of force, square meter is a unit of area, and a Newton is the same as the kilogram meter per second squared. So we won't get into that in this course, but if you take like any of our physics classes, that issue about like measuring pressures, we'll deal with what the fundamental units are. So you just need to know what to say here, but it's unit kilopascal. So these are equivalent values. An atmosphere is the same as 101.3 kilopascal. It's the same as 760 millimeters of mercury. Sometimes it matters what unit you use, and sometimes it doesn't. But what you can't do in a problem is have a mixture of units. So for instance, like if you know that some kind of starting pressure is 1.5 atmospheres, and the goal is to figure out like a final pressure in the unit millimeters of mercury, you can get your answer in atmospheres, but then you'd have to convert it from atmospheres into millimeters of mercury. So these values that are equal to each other can be used as conversion factors. So for instance, if you want to relate atmospheres to millimeters of mercury, there are one of 2 conversion factors, because in conversion factors, the value in the numerator and denominator are the same. So you can write an atmosphere over 760 millimeters of mercury, or you could also write it as 760 millimeters of mercury is the same as 1 atmosphere. I'll show you in examples why and how you'd have to do that. Volume, you can usually measure it in a bunch of different units. In the laboratory, like this Huffman apparatus, there are volume marks on it in milliliters. We usually use volumes in milliliters or liters. And then there's an issue about temperature. In all the gas law problems, temperatures must be in Kelvin. And early on in the class, you did some conversion work to get between units of temperature. A temperature in Kelvin is always a temperature in Celsius plus 273. And we absolutely never use Fahrenheit. Fahrenheit's not really useful at all in science. So pressure can be any of these 3 units: atmosphere, kilopascal, millimeters of mercury. Volume could be a bunch of different things: liters, milliliters, cubic meters. It doesn't really make a difference. Temperature must always be in Kelvin. So the freezing point of water, 0 degrees Celsius, to get that into Kelvin, you just add 273. So that's 273 Kelvin. Room temperature is about 20 degrees C. So that's about 293 Kelvin. And the reason why the Kelvin scale is important to use is that in Celsius, you can have negative temperatures, but because temperature is really a measurement of the average kinetic energy of particles, and it always has to be positive, it actually makes no sense to have temperatures that are truly negative. So the Kelvin scale begins at 0, as absolute 0, and goes up, and there's no such thing as negative temperatures in Kelvin. There's negative temperatures in Celsius and Fahrenheit. Okay, so Robert Boyle, in 1662, he was born in Ireland but lived in England, is famous as one of the fathers of chemistry, and one of them is related to this apparatus where he first described the idea that water's formula is H2O, there's two hydrogens for every one oxygen, and contributed this important idea about the behavior of gases, that there's a relationship between the pressure of a gas and the volume of a gas. So Boyle's Law, named after Robert Boyle, Boyle, that's pronounced the same as like to boil water, but boil water is like Boil, and those have no relationship to each other. They're just homophones. They just happen to be words that sound the same. His last name is Boyle, and the way I remember which law is Boyle's Law is kind of like backwards, sort of. All the other laws have temperature in them. When I think about boil, I think about it's hot and it has to be a high temperature, except this law just doesn't have a T in it. But other people remember Boyle's Law because you have to boil things at some temperature, and that temperature is at 1 atmosphere of pressure is a constant temperature. So it turns out that when you compress a gas, the volume decreases. So like if you have some volume of a gas, here's like a container, and we have a piston in the container, and there's some kind of a gas that's below there, I can compress the gas by exerting a force down on the piston. And whenever I do that, the piston will move down, and I've squeezed the gas into a smaller space. And as a result of squeezing the gas into the smaller space, I got to put more particles in a smaller amount of volume. And the pressure of the gas comes about from these collisions between the particle and the wall and the piston. So here I have a relatively high volume and a relatively low pressure. But now whenever you squeeze the gas down, you have a relatively low volume and a high pressure. And that's what this law describes, is that there's some kind of condition 1 and some kind of condition 2. So what P1 and V1 mean is that this gas here begins at some pressure and volume, P1 and V1, and the product of the pressure and the volume to start is the same as the product of the pressure and the volume when you're done. Those pressures and volumes are inversely related. So if you increase the pressure, the volume has to go down. If you decrease the pressure, the volume has to go up. And we're going to do some experiments. Let's see, Friday and Monday. We're going to work with some volumes of gases, change some pressures and volumes to see like what happens to the relative pressures and volumes in the laboratory to see if it matches up with the law. So this is like chemistry before chemistry was even chemistry. We're talking like the middle 1600s. Amadeo Avogadro's periodic table is like not till like 1820. The other gas laws weren't developed until the late 1700s. So this fundamental idea that pressure and volume are inversely related is about as OG as you get in chemistry. It's a physical change really. So it applies in meteorology, it applies in physics, it applies in chemistry, it applies in like, you know, your own breathing and stuff. All right, so here's some examples of things you can do. You got a balloon and it's got some gas, and where it's some kind of a pressure. So this description of the problem, if you need to identify what the units are and what they relate to. So 30 liters, what's 30 liters a unit for? Pressure, volume, or temperature? Volume. So this 30 liters, you can call that a volume, and we'll call that volume 1. In other words, volume at the beginning of the problem. 100 kilopascal, what's that a unit for? Pressure. So the starting pressure is 100 kilopascal. Now, if the balloon goes up into the atmosphere, atmospheric pressure is lower higher up because there's less atmosphere pushing down. So if there's like a mountain or whatever, and this balloon goes up to a higher altitude, it goes up in the air, the pressure is lower. So do you think that it would expand or would get smaller? Like what would happen to the balloon itself? Yeah, it's going to expand. One way you can think about that is there's an equilibrium on this wall where there's air pushing out and air pushing in. And if you go higher up, it'll get larger in size. Let me just get rid of my mountain. So like here it is higher up. It's bigger in size because at low in the atmosphere, there's a pressure from the atmosphere and a pressure from the gas. When we go higher up, the pressure has been reduced and the volume will increase. But what you know is that this new pressure is 25 kilopascal. And the question is, what is its new volume? So what is V2? V2, like question mark, you don't know. The volume was 30 at 100 kilopascal. We go higher up in the atmosphere, the pressure decreases, that causes the balloon to expand. So pressure goes down, the volume goes up. What you do is you take the law, P1 V1 is equal to P2 V2. And if you draw like a little diagram and show like, here's my starting pressure and volume and my final pressure and volume, but I don't know the final volume, you're trying to solve for V2. So to get V2 by itself in the equation, you can divide both sides by P2. So that looks like P1 V1 over P2 is equal to V2. And you just plug the numbers in. So if the final volume is equal to the starting pressure times the starting volume divided by the final pressure, that should get you the final volume. It's just very simple algebra. So you go P1, 100 kilopascal, times 30 liters divided by the final pressure, 25 kilopascal. Now, the math just goes 100 times 30 divided by 25, and the units of kilopascal will cancel out, leaving you the unit liter. So whatever volume unit you start with is the same as the final volume unit. So it's going to be 4 times 120 liters because 100 divided by 25 is 4, and 4 times 30 is 120 liters. I got to let you in on a little bit of news. If you take and have a helium balloon that's completely full and you attach a note to it and you let it go, don't think that it goes way up in the atmosphere and gets carried to some other state or country and gets delivered to some other kind of person. Because pretty much not long after it goes up and goes out of sight, that volume wants to increase as the pressure goes down and it pops. And then the pop balloon just falls back to the earth. Usually, you know, within a mile or so where you let the thing go. And then it's litter. A deer comes along and snacks on it. That's disgusting. So that's that deal. Other things that you can, I'll show you a thing about a high altitude. So let me do, what's his name? I'll show you tomorrow. I've got a set of pictures about it. Okay, other things, you can buy gases in compressed cylinders. So like, you know, like this is a cylinder of carbon dioxide gas. Use that with the aquarium systems. Carbon dioxide gas is compressed, put into the bottle, and this is at like 250 pounds per square inch, so it's about 10 atmospheres of pressure. In other words, the volume of gas in there is about 10 times greater than it is at atmospheric pressure. Except there's another trick, and the carbon dioxide is actually converted into a liquid. So the volume of carbon dioxide is about 1,000 times the volume of the container itself. So instead of having 1,000 of these with 1 atmosphere of carbon dioxide, you can have just 1 of them, and it has the volume of 1,000 bottles, but it's all compressed. Whenever you decrease the pressure, the volume has to go up. So here's like a container, it's got maybe some gas in it. We got a bottle of gas. That's a mess. So an anesthesiologist may use an anesthetic gas, or like you go to a dentist and they may have you on like nitrous oxide. It's like they call it laughing gas, and it kind of like knocks you out, so you can do a little bit of dentist whatnot. The pressure in here is high, and the pressure is going to drop. So as a result of the pressure dropping, the volume should go up. So here's a way to read it. 2.50 liters, that's a volume. So you got some kind of volume, 2.50 liters, and that volume is going to change or the pressure is going to change from 100 kilopascal to 40 kilopascal. So this starting pressure is 100 kilopascal. Whenever you let the gas out of the bottle, if you were to let all this gas out of the bottle, it could take up a lot of space, much bigger volume. Because this gas is compressed, it's high pressure, it's low volume. When the gas escapes, it can end up with a lower or a larger volume. So now there's a new pressure, 40 kilopascal. And you're looking for what's the new volume? V2, you don't know. So the law is P1 V1 is equal to P2 V2. You're trying to figure out what V2 is. So to get V2 by itself, you divide by P2 again. V2 is P1 V1 over P2. So the starting pressure was 100 kilopascal. 2.50 liters divided by 40 kilopascal. Six and a quarter. And then those volumes of the gas can then be used if you adjust it to standard pressure. You can then use it with Avogadro's law, that every 22.4 liters gets you a mole of a gas. So if this 6.25 liters happens to be at standard temperature and pressure, then you've got a quantity that's in moles. The 2.5 liters, because it's not at a standard pressure, well, this is actually at standard pressure, you end up with a different number of moles of gas for in the chemical equation. All right, so another law, Charles' law. So Charles' law is named for Jacques Charles, who's a French scientist. And this description was provided in about the 1780s. So that's about 120 years after Boyles' law. This is right around the time of the formation of our country. And it turns out that a bunch of these laws with gases are related to work done by the French. French scientists were totally into electricity and gases. You may know that the French were obsessed with hot air balloons and aviation in the early days of aviation. So it's Charles' law, and when you have the possessive of a word that ends with S, usually it's just S apostrophe, but then most commonly in English, if it's possessive of a proper noun, then you get an extra S on the end. So it's not incorrect to say like Charles's law, but you also see it written as, Charles with an S, with just an apostrophe after the S. But it's more proper because it's a proper noun to throw an extra S at the end. So Charles' law is the relationship between volume and temperature. And the way to write this law is V1 over T1 is equal to V2 over T2. So instead of the product of volume and pressure, it's the relationship between volume and temperature. If you change the temperature of a gas, the volume of the gas will also change, so long as the pressure is constant. So what's not in this equation is pressure. It's very important that temperatures must be in Kelvin. So these temperatures, they cannot be in Celsius. They must be Kelvin temperatures. Kelvin only. The volumes could be anything. The volume could be anything. It could be milliliters, could be liters, could be gallons, could be cubic meters. It could be anything. It doesn't matter what the volumes are, but what is important is the temperatures have to be in Kelvin. You cannot have any volume different than Kelvin. Here's an example, a practical example of that. Here's like your car, and it's like it's the fall, so maybe the temperature is like 70 degrees Fahrenheit, and the tires themselves have gas in them. And you typically want the pressure in car tires. It depends upon the vehicle, but around 30. The common unit we use in this country for pressure is the unit PSI, pounds per square inch, which is another pressure unit, but we don't use it in chemistry. Um, then it gets to be the winter time. So you get a really cold day. And what happens when the temperature drops down is the pressure of this gas will go down. So if you check your car tire pressure on a nice warm day, the pressure might be nice and high. But then if the temperature gets lower, the pressure will go down. So maybe now the temperature is 10 degrees Fahrenheit, and you'll find that the pressure is less than 30 degrees or less than 30 psi. The pressure has dropped down. Similarly, if temperatures of gases increase, the pressures go way up. So like there's a risk, like if there's a fire in a home and there's some kind of compressed gas in the home, oxygen tanks, um, sealed containers that have aerosols and things. And if a fire starts and those pressures go up, those containers will start to blow up, will start to explode. That as the temperature goes up, the pressures go up, and it can cause a break in the container itself. Okay, so what happens if the temperature increases as for a fixed volume of something? All right, so here is some gas. I got 10 liters of the gas. So this is like a starting volume. And the temperature is 20 degrees Celsius. And then we're going to heat the room up. And as a result of increasing the temperature, hey, you're doing gas laws.
Nice.
How's it going, man?
Good.
Never see you around.
I know. I usually don't leave my zone up there because I've got so much going on. So, for what? Because this is the first time I make copies this year with paper. I use paper.
It's amazing.
This is what this is. Oh, you guys have it. Never mind. My students don't know what paper is.
Yeah. Remote students have a hard time with it. Yeah. Sometimes it's easier to do stuff on paper.
Yeah.
We got axolotls in the next room. Axolotls? We're feeding excess ones to clownfish because they like Mexican food.
Oh, really?
Yeah.
It's not too spicy?
Yeah, the axolotls are a little spicy, but
okay.
Yeah. All right, now here's the thing to know. It looks like at first glance that this temperature doubles from 20 to 40. But the thing you got to be really careful about with temperatures, whenever you talk about temperatures, is this temperature hasn't doubled. The number has gone from 20 to 40, but the true temperature has not doubled. And that's because the temperatures must be an absolute temperature. So, to get it in Kelvin, you add 273. So this is 293 Kelvin. And when you add 273 to this, you get 313 Kelvin. So the temperature has not doubled. The temperature has only gone up from 293 to 313. So anyway, if you go V1 over T1 is equal to V2 over T2, to get this new volume, you want V2 by itself. V2 is going to equal V1 T2 over T1. 10 liters times 313 Kelvin divided by 293 Kelvin. The volume doesn't double because the temperature doesn't actually double. It goes to 10.7, like 10.7 liters. It isn't a dramatic change in the volume. All right, anyway, you should take a look at this up close, but this is where that arrow was at the beginning, and now it's much lower. So, we only got like a minute or two left. But come up so you can see the bubbles. The bubbles are extra super tiny. They're the tiniest bubbles you've ever seen in your life. They're like microscopic. They're almost like a fog going up through the water. It's pretty cool.